Okay, I want to do another video here on the applications of eigenvalues and eigenvectors. Okay, spectral theory, quote unquote. Let's talk about something interesting called the Matrix Exponential. At least I think it's interesting, and hopefully you will think so as well. We need to go and talk just a little bit about differential equations. Okay, so let's come back. Hopefully you've been exposed to this one way or another. Alrighty. Suppose that x is actually a function of t. Say t is time, maybe. Okay, so x equals x of t. That's what I mean by that. And in fact, x is going to be a differentiable function of t. Okay, so dx over dt is, in this differential equation, just a constant multiple of x. Okay, so the rate of change of x with respect to, say, time is just a constant multiple of x itself. And then I'm going to have some sort of initial condition here. Now, if you've exposed to differential equations at all, and you can probably guess what the answer is going to look like here. What function is equal to its own derivative? Yeah, the non-trivial one would be the exponential function. That's almost what we're dealing with here. Okay? Let's talk about a method from differential equations called separation of variables. Okay, I'm going to put the x's on one side and t on the other side. Okay, so they're separated here. And this whole method can be justified here. I'm going to be doing anti-differentiation on each side. So you see on the left-hand side, I get the natural logarithm of the absolute value of x. On the right-hand side, I get at plus an arbitrary constant c there. Okay, let's go e to both sides there, and I would get the natural logarithm of x is e to the at plus c. And I can break that up into the product of e to the c times e to the at. Okay, and then I can get rid of absolute values by going plus or minus here on the front of this expression here. Now, e to the c plus or minus is simply a constant. Okay, so k here is going to be simply a constant. Okay, so this is the form of my answer. Notice that the exponential function does indeed appear in this answer here, but it's actually what? In the exponent, I've got not e to the t, but e to the at, and I've got this arbitrary constant multiplier out front. It's not totally arbitrary, this constant out front here, though, like you would expect from an anti-differentiation, because we also had something we call this initial condition. Okay, x naught is some value here. Okay, we said the initial condition was that the original x value, in other words, x at the value t equals 0, should be this x naught, whatever given that value is. It's some number. Okay, now since x in general as a function of t time, say, is given by this formula, in the case where I'm letting t equal 0, I would have x of 0 is equal to x at 0, which is k e to the a times 0 power. Notice e to the a times 0 is e to the 0. That's just 1. So 1 times k is k. So in fact, the constant that goes out front should actually be what? The initial value of x. So we would say the solution to that differential equation, this guy, it's an initial value problem, but the solution to this is that. Okay? And you can always double check, right? You could always double check. Differentiate this with respect to t, and all you'll end up doing is multiplying the original function by a. So that's what you would get. It would satisfy this part right there, the derivative part, and indeed this thing at 0 is equal to x naught. Okay, so this is the solution. In fact, we can show that's the unique solution. Okay, alrighty. But here we had this where what? A function of t was just a constant multiple of the original function, okay? And that led to what? An answer which was an exponential, essentially. Okay? Alrighty? Now, what we're going to talk about and use some of our matrix and eigenvalue methods and stuff on is systems of linear equations, okay? With constant coefficients. They're going to look like this, okay? I'll give you an example and you'll have some exercises to do along these lines. Okay, now this time I've got two functions, both x and y. They're both functions of t. Okay, now x prime of t, or dx over dt, if you like that language there, if you like the Leibniz notation. Okay, the instantaneous rate of change of x with respect to t. If we say t is time, we could say the instantaneous rate of change of x with respect to time, or that abstract speed, is this. It's, for this example, it's going to be 6x plus 2y, and here the rate of change of y with respect to t is going to be 4x minus y. Notice these are scrambled together, okay? So the rate of change of x with respect to time is what in terms of both x and y, and the same thing with the rate of change of y with respect to t. It's a function of both x and y. Okay, so that looks kind of tricky here. Okay, oh, we're going to throw in some initial conditions also. I claim that x at time 0, or t0, is 1, and y at 0 is 8. Okay, I'm going to throw that in. So this would be an example of a system of linear equations, okay, with these constant coefficients here. Okay, these type of problems could get much, much worse. These could be much worse functions of x and y, but that's why people study differential equations, right? All right, now what I'm going to do here, though, I'm going to jump to my little prime notation, just make it a little tighter here. I'm going to say x prime of t and y prime of t instead of using the Leibniz notation. But I want you to notice that I could, if I make this into a vector, okay, a column matrix x prime y prime, then I could actually write this. X prime y prime is the square matrix 6, 2, 4, negative 1 times the column vector xy. A simple product of these two, this matrix and this column matrix here, ends up giving you this side over here. You can see I'm not lying there. Okay? Now I'm going to go ahead and let A represent this matrix here, the square one, 6, 2, 4, negative 1, reading across. Okay? Okay, now I'm going to think about my unknown, in this case, in vector terms, right? This is linear algebra. So I'm going to call this V bar is x, y. Okay, now these are functions of t. Okay, so this is a vector of functions, right? But I'm going to give it a single name, so this is really a function of t, but I'm going to give it a single name, V bar. What we could actually write then is the derivative of V bar with respect to t, which I define this way, we haven't really done that before, is if I differentiate a vector with respect to t or something, some scalar, I'm just going to differentiate both the components or the entries of that vector with respect to t. And you see that would give me the x prime, y prime. Okay, but dv bar over dt would equal my a times v bar. Okay, and v bar at 0 would be the vector what? 1, 8, because that was my initial conditions up there. Okay, so you can see this looks very much like my original problem up here that we did previously, example 1. It looks a lot like that now, but instead of a single function, I've got a pair of functions, but it's written as a single vector. So I've got dv bar over dt equals a constant matrix this time, instead of just a scalar, times v bar, and then v bar at 0 is given by 1, 8 there. Okay? All right? Now, let's come back here. Let's look at our original solution to the previous problem. Our solution ended up being what? X was just the original value of x times e to whatever that scalar multiple was times t, which we'll call time. Okay? That was the solution to this one. Okay? How about the solution to this one? Could this solution look something like this? V bar equals e to the at, where a is that square matrix, times this vector 1, 8. Notice this initial value vector has to be written over on the right-hand side. Otherwise, what? The left and right hand sides would have different dimensions, right? Okay? So up here, analogously, I would have had to take the x naught and do what? Move it over on this side. But we don't usually do that in algebra, right? We go 7x, not x7. It could have been otherwise, but just historically, this is what's happened here. But my linear algebra would be forcing, if this has any meaning at all, it would be what? First of all, forced over on this side. The initial vector would be over on the right. Okay? Alrighty? But let me just, what could this possibly mean? E to the AT, where A is not a scalar anymore, but where what? A is this 2 by 2 vector. It's a square matrix, or 2 by 2 matrix. What in the world could that possibly mean? Okay? Well, that's why we're talking about the matrix exponential. In fact, this is the solution to this system of equations up here. And I'm going to show you explicitly what the solution is. Okay, this does solve this. But I have to define this correctly. Okay, e to the AT. I have to define that thing correctly. That's what we call the matrix exponential. Now, how are we possibly going to define something like that? It looks crazy, but it's interesting here. Hopefully you find that interesting, how we could extend that. Okay, the Maclaurin series expansion. Oh yes, you remember actually how we actually compute e to the z. Okay, I'm not using x or y, I'm using z here, because this actually works also for complex numbers, by the way. Something you probably haven't had yet is complex analysis, where these are allowed to be complex values, a plus bi. Okay, you can think of these as real if you want. We're going back to what? Calc 2. Okay, remember power series expansions, how much you love those? Well, e to the z is hopefully something you remember. That would be what? Z to the 0 over 0 factorial. Z to the 0 is defined to be 1, even in the case where z is 0, by the way. Okay, but that's z to the 0 over 0 factorial. You remember 0 factorial is 1. Okay, so all this stuff boils down. It's a fancy way of writing 1. I'm going to show you why I want to retain that term, though, in what I'm going to be doing, even though it looks trivial. Okay, the next term, do you remember, was z to the first power over 1 factorial. And the next term was z squared over 2 factorial. And then I go plus dot 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 plus ellipsis, because this just keeps going on in the same pattern. I could have written it more compactly with the summation notation, but this is easier, I think, for you guys to see, because you're recalling this stuff from Calc 2 here. And this actually held for what? For all z, any real value of z, and it turns out any complex value of z also. Again, you haven't had complex analysis probably, but let me just state that's the truth. Okay? So e to the z is always equal to what's on the right-hand side of that equality there. Okay? Always. Now, here's what I want you to think about here. What am I attempting to do? I'm attempting to compute e to the AT power, where t is just a scalar, right? But A is a square matrix. In this case, for the problem we had above, it's a 2 by 2 matrix. But in general, it's going to be a square matrix. Okay, possibly higher dimensions. What if I was to just formally replace z by the quantity a times t? Then e to the AT would be AT to the 0 power over 0 factorial plus AT to the first power over 1 factorial plus AT squared over 2 factorial plus so on and so forth. Okay? Now, I'm going to declare the following. A times t, because t is just a scalar, a times t is also a 2 by 2 matrix. If I raise it to the 0 power, I'm going to declare that to be the what? 2 by 2 multiplicative identity. And since 0 factorial is 1, I declare that first term to be what? 1001. Okay? Now, let's look at the next part. This would be a to the first power over 1 factorial times t, right? And the second part would be what? Since t is just a scalar, I could take the scalar t squared out here, and that would be a squared over 2 factorial. And then what? A cubed over 3 factorial t cubed, and so on and so forth down the line. what would this be? The first term would be a 2 by 2 matrix. The second term is a 2 by 2 matrix. The third term is a 2 by 2 matrix. The fourth term is a 2 by 2 matrix, all the way down. Or if some people might like call this the 0th term, the first term, the second term, the third term, that way the powers would actually match. But whatever. The point is I could actually imagine the sum, remember the sequence of partial sums, okay, that actually correspond to this whole summation. Okay? The sequence of partial sums would exist, right? They would be what? A sequence of 2 by 2 matrices. The first term would be this. The second term of the partial sums would be the sum of the first two. The third would be what? The sum of the first three, and so on. But you would have to worry about what? Convergence, right? The convergence of that sequence of partial sums. Now, we haven't really talked about convergence of sequences of matrices, but the idea is very simple. A sequence of matrices, all of the same dimensions now, is going to converge if what? The sequence of any particular entry for all the entries is going to converge, okay? So, in other words, the position, so if I have a sequence and I think about the sequence of entries in the upper right corner or the upper left corner, that sequence as just a sequence of numbers has to converge. How about the next term, okay, or the next entry, okay? If I imagine that as a sequence, right, from the sequence of partial sums, if that converges, then I've got convergence, okay? Okay? So I hope you understood what I meant. So you're just looking entry-wise if you're getting convergence, okay? Just entry-wise, you're getting convergence in the sequence of partial sums, okay? Let me show you this, okay? Now, we're not going to go through entire proofs here, but we can actually show that this sequence, in the sense I just mentioned, for all square matrices A and values of t, actually converges. Yep, you actually get a finite answer out of this. You get a 2 by 2 matrix answer here, which is the limit matrix, okay? I should really call it S for sum, but it's going to be a 2 by 2 matrix, okay? I don't know what the limit is, but we're going to find out. We'll actually find out what that limit is, okay? Or the reason why this happens, by the way, is because although the terms might be growing exponentially in the various entries of the matrices, making up, right, all the terms of my series here, they might be growing pretty fast. But remember, just like in Calc 2, I've got this powerful, what, factorial growth in the denominator. And that crushes, what? Crushes the entries in the powers of A. It crushes them down quickly. Remember, that's what you need for convergence, right? You need the terms of the series to, what? Drop sufficiently quickly to get a finite answer, okay? Factorial growth helps out greatly, okay? So the numerator looks very impressive with exponential growth, but that denominator still crushes it, okay? Factorial growth, very dangerous, okay? All right. Now, what would happen? Term-by-term differentiation with respect to t will show that expressions like what I have above, that, will actually satisfy the system of differential equations under this definition of the matrix exponential. That's just a no there. Okay? Under this definition of the matrix exponential. Now, however, you might think about this. Computing the matrix exponential looks tedious, like this. Okay, we're actually going to do this for this one up here. See that A? We're actually going to compute what this is. What this is, rather. Okay, what that is. Does that look tedious? Okay, yeah, that looks like a lot of work. Okay, something for a computer. But we're going to do it by hand without a computer. Okay, I'm going to show you what's going to happen in the case where A has a diagonal form. In other words, it's diagonalizable, okay? In the case where it's diagonalizable, and you'll have questions of that type in your homework, okay? we can actually cut down on our work greatly. Okay? And I'm going to show you how that works here. Suppose A does have this diagonal form. So A is P times D, where D is diagonal, right? Times P inverse. Okay? All right? We're attempting to find this, right? Now I'm using my summation notation, and I have my powers written as K. The summation K goes from 0 to infinity. Okay? Here is really my A to the K power, right? Okay, that's really my A being raised to the K power divided by K factorial times T to the K, right? All righty, so that's all we're doing. But I hope you remember that we could actually do this. P times D times P to the minus 1, or inverse, to the K is actually equivalent to what this? P, D to the K, P inverse. Remember how the K can migrate down into the, what? Onto the D. And computing power of a diagonal matrix was really easy. Remember we did this before? So if I substitute that fact up here in my previous expression, I've got e to the at equals the summation K goes from 0 to infinity, P D to the K, P inverse over K factorial, D to the K. And now I'm going to actually factor out these two matrices. That's just a constant matrix, which I'm going to, because it's multiplied on the left, I'm going to factor it out on the left, so it pops out. And likewise, these are just, that's a scalar, that's just a scalar, so I'm going to take this fellow, P inverse, which is on the right, and it's going to pop out of the summation also. Again, it's just a constant matrix. And I'm going to retain what's left. And then on the inside of the parentheses here, I've got the summation K goes from 0 to infinity, D to the K, K factorial, T to the K. Okay? Now, you remember what D looked like? D, when we, diagonalized the matrix, D, that diagonal matrix, was actually what? A diagonal consisting of eigenvalues of the matrix A that we were dealing with. So what I've done here is write D equals lambda 1, lambda 2, down to lambda n, in general, zeros everywhere else. If I go D to the K power, then remember, because this is a diagonal matrix, then all I'm doing is taking all the, entries down the main diagonal and raising those to the K power. Zeros go everywhere else here. So if I imagine that happening in a summation right above expressing e to the at power, then e to the at would be p times what would happen if I sum all those up. Because I'm just looking at those summations entry-wise, I would be what? It would be taking my series, and for this entry right there, I would be going what? The summation K goes from 0 to infinity, lambda 1 to the K, over K factorial T to the K, but we already know from what? Real numbers or complex numbers even, that that is precisely that. Okay? That's our regular series expansion for e to the lambda t. Okay? So you see what I'm getting right here? That's really e to the lambda t. Now I'm doing that all the way down the main diagonal. So what I actually have is what? E to the lambda 1 times t, e to the lambda 2 times t, so on and so forth, e to the lambda n times t down the main diagonal, zeros everywhere else, p, and then on the right multiplied by p inverse. That's what e to the at is. Ta-da! Okay, so we've now defined how to compute a matrix exponential. Let's give it another dimension here. Okay, and now we're going to apply this to a problem here. Now, this is assuming it's diagonalizable. Okay, let's go back and revisit my, my problem 2 here. Okay, so I have x and y as functions of t, and then I had x prime equals 6x plus 2y, y prime equals 4x minus y, and then we had these initial conditions. X at 0 is 1, y at 0 is 8. Okay, we said we could actually write this as this matrix equation here. Okay, alrighty. And we said it would have this solution here. Okay, and the x naught, y naught is actually 1, 8. So I could substitute those in there. Okay, but I will do that at the end here. I'm not that concerned about that. I need to compute what? E to the AT. Okay, now we've got a specific A this time. Now what I need to do is think about this in terms of a diagonal form. There I had it. Okay. Okay, I need to find that diagonal form though. All right. If you actually go through, you have to go through to diagonalize this and go through it. You find that this this matrix A that we're working with up here. Where'd it go? Here it is. This matrix A has eigenvalues 7 and -2. Okay? And then you can go ahead and find corresponding eigenvectors. 2, 1 corresponding to 7, and 1, -4 corresponding to -2. So we've got P reading across 2, 1, 1, -4. D, 7, 0, 0, -2. P inverse, that's easy to compute. I factored out the 1/9, okay? But it's 1/9, 4, 1, 1, -2. Okay? Explicitly, I've written what the eigenvalues are because remember, we're going to be using this formula up here that we developed, that guy. Okay? Let's actually compute what e to the AT is. That would be P times e to those eigenvalues down the main diagonal. Don't forget the t on there, by the way. I should say the multiples of the t multiples of the eigenvalues. P inverse. Okay? I factored the 1/9 out in front of everything, by the way. Being a scalar, of course, we can just do that. So I put the 1/9 out front. But here we go. We've got what? Here's our P. Okay? Then we've got what in here? E to the 7t, e to the -2t. And then we've got what? P inverse with the 1/9 factored out. Okay? Then I just multiplied these, leaving the 1/9 out of there. Okay? Just multiply these three together. A totally mechanical operation. Okay? Multiply it by the 1/9, then multiply by the original conditions, right? Remember the form of our answer? Okay? The form of our answer. And then I did a little simplification at the end, and we get the following answer. Okay? X of t is 8/3 e to the 7t minus 5/3 e to the -2t. And y of t was 4/3 e to the 7t plus 20/3 e to the -2t. Now I've substituted those back into the original equation. I didn't show the work there. And this actually does end up satisfying our original differential equation system up here. It works, in other words, okay? It actually does happen. Okay? All right. Now there's other methods that we can use, okay? Besides the method I showed you with the matrix exponential. But this is pretty cool. Hopefully you think it's kind of neat that you can go e to the power of a matrix. Leave you just with a couple quick questions here. Could I go the sine or cosine of a matrix like this, AT? Okay. Alrighty. Could I do something like that? Maybe sine or cosine? How about the natural logarithm of AT? Could you do something like that? Okay, the clue would be to look at what? Series expansions again. Okay? We would expect this to probably converge everywhere. This, no way. This is probably has a very restricted type of convergence here. Okay, being natural logarithm. Anyways, I hope you understood that and that you're ready to, after your reading as well, tackle some of those problems. Okay?